Hello viewers, welcome back to my channel. I hope you are enjoying all the videos that I am uploading. If you haven't subscribed to my channel yet, please go ahead and subscribe to my channel and also share among your friends. Today's problem is LRU cache. So we are asked to design a LRU cache. Design and implement a data structure for least recently used cache. It should support the following operations: get and put. Get the value will always be positive of the key if the key exists in the cache, otherwise return -1, right? So get is if the value is existing, it will return the value, otherwise it will return a -1. Put key and value, right? Sets or inserts the value if the key is not already present. When the cache reached its capacity, it should invalidate the least recently used item before inserting a new item. So basically we are asked to put a set of key value pairs into the cache, right? But when the cache size is at its capacity, right, we should invalidate the least recently used item. So least recently used item, we will go look at the definition for that in a bit. So once the cache reaches to that capacity, we should remove one of the items which is there in the cache and insert a new item. So that's how the LRU put will work. So the cache is initialized with a positive capacity. So that means it is a positive number, right? So and another follow up here, we are asked to do these operations in order of one time complexity. That means a constant time complexity, right? So basically, let's try to understand what is the LRU cache definition, right? So it says least recently used. So for example, you have been inserting key and value pairs into the cache, right? So when it's not just inserting with the put operation, but there is a get also. So when you try to get a key, what is the key which is not accessed for a long time? So that is what is the LRU cache, right? So what is the key value which is not accessed for a long time? So that will be evicted when a new key was asked to put, only when the cache is already full. If the cache is not already full, you just keep on adding it. But if the cache is full, that is when we need to evict a particular key value, right? So let's go ahead and look at the example one, try to understand the concept here, right? So LRU cache, so he's initializing with a capacity of 2, right? So that means it can store only 2 key values, right? So now, so cache put 1, cache put 1 1, so key is 1, value is 1, cache put key is 2, value is 2, cache get is 1. So that means 1 is got, 2 is not referenced yet. And now cache put 3 3, right? So 1 is recently used, 2 is not used. It has been put into cache, but it is never used. So now we are asked to put the 3 3, right, in here in the line 4 here. In this case, what will be evicted? Since 1 is used, 2 is not at all used, right? That means it is not used at all. In that case, what you are going to do is evict 2, right? So that is what is going to evicted. So after that, he's trying to do a get operation on the 2 if it is present or not. If it is present, then we have done some mistake or something in the code, right? So it should return -1. That means it's not found anymore because that has been evicted with the put 3 3, right? So now cache put 4 4, right? So what is the one which is recently least recently used now? So in that case, 3 has been just put now, right? So and 1 is also been used, but in this case, what will be the thing that we need to remove is we have to evict 1. So that is how it is going to work, because 1 is not used. It has been used once, but after that it has not been used. So it will have to evict 1. So now if you try to get a cache of 1, right, it should return a negative. So cache get 3, it returns 3, cache get 4, it returns 4. So basically That's how the algorithm works here, right? So that's how the design should work in different sense. So least recently used is the element which has not been accessed for a long time. So from the examples that is given here, right, whenever we are asked to put 4, it should evict 1. So this is the key thing that we have to keep in mind while designing the code for this, right? So let's go ahead and try to understand and look into the strategy that we are going to implement for this, right? So least recently used, as we talked about the definition, in other words, which is not accessed for a long time. So the key value pair which is not accessed for a long time, that will be the LRU, right? As long as we have a space in the cache, we just keep on inserting it. But once the space is exhausted, we need a candidate that need to be evicted from the cache, right? So that is the important part in determining this cache. And also keep in mind that we are going to solve this problem with constant time complexity, right? So in order to support the constant time complexity, we are going to choose several data structures, right? So normally when someone asks you to do something in constant time complexity, right, basically the two operations that here are get and put. So these two operations in order of 1. So one, you can think of a hash table is the one which can do gets and puts in order of 1 time. That is a constant time, right? So we are going to use a hash table for this in order to solve this or design this LRU cache. So that's one data structure we are going to use. And how are you going to keep track of the LRU key, right? So LRU key value basically, right? So there are several data structures that we could employ. We could use a queue, basically a first in first out mechanism, right? But can queue be used efficiently in that case? Because if whatever you first insert, it may not be the first to get accessed, right? So in that case, queue probably is not the right data structure that we can use. And other data structures like stack actually doesn't fit in this scenario. And there is something else that we are going to use for designing this problem. So I'm going to use a linked list. So basically we will see how linked list is more efficient than a queue or a stack for this problem in a bit, right? So I'll use a map and I'll use a linked list. So these are the two data structures that we are going to use. And as we said, we have to fetch the LRU key in order of 1 time, right? So we need to fetch the value in order of 1 time, right? So what we are going to do in this case is what value has been used recently, what key has been used recently. For just to keep track of those two, we will have a reverse map. That means key to value and value to key. So that's how we are going to use. So a map will have key to value, and a second map we are going to use is value to key. That is, we are going to call that as a reverse map. Okay. So the data structures that we are going to use in order to solve this problem are 3: a linked list, a map, a reverse map, right? So map and reverse map, you can just think of same, basically key to value and value to key, right? So these are needed in order to support the order of 1 time complexity. So if that is not a constraint, right, then we don't actually need the reverse map, right? So here we are going to use 2 maps and 1 data structure, that is a linked list. So let's go ahead and try to understand how we are going to use this, right? So we are going to use this passive capacity, right, for initialization. So there is a constructor, right? There is a constructor LRU cache here. So it takes integer capacity. So I am keeping that capacity in a private variable and initializing a new linked list, initializing a map, initializing a reverse map, right? So a linked list will have only, since the key values are integers, we just go with the integers, right? So linked list node will also have int type. So for this thing, all the data types are the incoming data and outgoing data is integer. So that is a safe way basically. just use integer. So that's how we have initialized the constructor, right? So let's go ahead and try to use the get operation, right? So when you go look at the description for the get operation, so as long as the key is existing in the cache, we have to return that key, otherwise -1. But while we do the get operation, right, we need to keep track of the least recently used, right? Whatever the thing that is least recently used. As and when a new key is put into the cache, we are going to add that key value pair into the head of the linked list. Okay, so that is one of the keys that we are going to use. So as and when somebody is putting a key value, right, we will put that into the head of the linked list. And if it is accessed, again, anywhere that is accessed, we are going to pull it out from the linked list and put as a head. So for this purpose, what we do is, let's try to understand the put scenario first and then come back to get, right? So let's go to put scenario first, right? And then we come back to get, so that it will be easy to understand, right? So put, we are checking whether the key is already there, right? If map contains that key, right? If it is already there in the key, what we are going to do in this case is, we will have to look up, right? Look up the linked list node from the map. So map will have key to value, right? And reverse map will have value to key, right? So that's the thing. So what we are doing is, so looked up here, in this case we are looking up from the key. That means the key is already present in the cache. In that case, what we need to do, this is probably they are trying to override, right? So basically a key value is present, but for the same key he is trying to insert a new value. So that is a possible operation here, right? So if in that case, what we are going to do is, we are going to get the corresponding value, that is a linked list, and remove that particular node from the linked list. Okay, so you remove that particular node from the linked list and remove that from the reverse map, because he's trying to put a new value, right? So we don't need to we don't need to keep track of that anymore, because the value is changing. And now what we are going to do is update the value of that linked list node and put it at the head of the list, right? So put it at the head of the list, because that is now being put with a new value, right? So put it as a head of the list. So add first is going to do the insertion at the head of the list. And then, so this is a new key and value pair now, right? Although the key is existing, but the value is changing, right? So this will be treated as a new key value pair. So what we are going to do is, you have to add this node, the linked list node, to the map, and reverse map you add linked list and key, right? So this is the reverse map. So in the map you are adding the key to linked list, and for the reverse map you are going to add the linked list to key. So that's what we are going to do in case the key is already present in the map. So it is just updating the existing key, right? This is just purely updating the existing key. So now let's say if the key is not present in the map, that means you are trying to use the space from the cache, right? So in that case, this is when you have to see if you are already at the capacity, if the cache is already at the capacity or not, right? So let's go to the else part, right? So that means that key is not present in the cache. That means you might have to evict in case the cache is full. If it is not full, you just add it. That's not a problem, right? So now linked list. So we are going to create a new node, new linked list with a value, right? So all we care is just the value, and if the map.count is at the capacity, right? So number of elements in the map is at the capacity. That means we are ready to evict 1, right? So what is that? What is that? The thing that we can evict. Now we go back to the linked list, right? So we go back to the linked list and see okay, the last element in the linked list, right? So the linked list last, that's what I'm going to get. So if you put at the end, as and when you are accessing or inserting the elements into the cache, right? So all those things are being put as the head of the list, right? At the head of the list. That's what the idea. So now we are going to remove the tail, that is the last tail of the list, and get the key from the reverse map. So this is where the reverse map is very useful. So now we know we are only storing the linked list node as integer. So if we store the key and value, probably we don't need to have the reverse map here, right? But if you only store a linked list node, right, we will need a reverse map, right? So now reverse map will have the last, that is the linked list node, right? So from that you get the key, right? So once you got the key, it's easy from the map to remove, right? And you can remove the this key and reverse map also that particular node. So from here you have emptied one space, right? And finally what you are going to do is remove the node from linked list also. This is how we are going to do, right? So remove the map and remove from the reverse map and remove from the linked list. All the three places that particular node is removed, right? And now what we are going to do is, since we have emptied one space, right, we are going to add that to the head of the list, and we are going to add to the map, and we are going to add the reverse map, right? So this is how we are going to do the put operation essentially, right? So there are two cases here. One is when the map is already containing the key but the value is differing, that's one thing. And if the map doesn't have the key, that is another scenario. But once you don't have the map in the key, there are again two scenarios. You have the cache is full or cache is not full. If the cache is not full, you just go ahead and add it. But if the cache is full, then we have to evict. So this particular thing, if map.count is equal to underscore cap, right? So that if loop is going to take care of the eviction for us, right? So let's go back to the get scenario now, right? As we are saying, if anything that is get, we are going to put into the head of the list as long as the key is present. So now, so get operation is, if the map contains key, then only we are going to check the cache, right? Otherwise, as per the definition, we are going to return a negative one. Yes, otherwise we are going to return a negative one. So if the map contains key, then, so what is our savior here? We are going to get the key from the regular map, and for which we get a linked list node, right? So we remove the linked list node from its position, wherever it is, and put it to the head, right? Put into the head. So it removes the position from that linked list and puts as the head. So that means it is recently used, not released recently. So it is recently used. So all the recently used items will be at the head of the list. So that means the tail will have least recently used. That is the node which is used very far in time, right? So that is the reason why we are doing the linked list last in put, right? If you go look at the line 64, right, that is what it is going to take care. So with this, we can support all the operations, the get put operations in constant amount of time. So we are using two maps and one linked list. So let's go ahead and, so we know the time complexity for the get and put is order of 1 now, right? So what is get is doing? It is trying to get, it is trying to see if the map has, otherwise it is returning 1. So this will be order of 1 operation anyway. So now it is going to get the thing from the map. So getting is again order of 1, and removing from the linked list is also order of 1, and adding is also order of 1, right? So basically that's how it is going to work. Okay, these are all order of 1 operations. Now let's go ahead and look at the space complexity, right? So we are using a linked list and two maps, right? So linked list will have the number of puts right? So whatever the traffic that we get, right, the number of puts, that will be equal to the cap, right? So worst case, the number of nodes in the linked list are equal to the size of the cap, whatever the capacity that we are initializing. So let's say the capacity is n, right? Let's say capacity is n, right? So in that case, the linked list will have n, right? And dictionary, the map will have n, and reverse map is also n. So there is 3 times of n space that is required, right? So 3 times of n space is required. So normally the maps will have 2 times of n plus 2 times of n and 1 time of n. So we could say 5 times of the n, right? So the total space complexity for this is order of 5n. Since we eliminate the literals from the big O notation, we would say order of n is the space complexity that we will be using for this particular algorithm. If you have any questions, please leave them in the comment section. I will get back to you as soon as I can. Thank you for watching. If you haven't subscribed to my channel, please go ahead and subscribe to the channel. I will get back to you as soon as I can for all your questions. And also, don't forget to click the bell icon. If you click the bell icon, you would get notifications for all my future videos. Thank you for watching again. I will be back with another problem from Leetcode very soon. Till then, goodbye.